Welcome, everybody. We are in Chapter 4, Section 1, Maxima and Minima. What is this all about? There's a lot of concepts that we will be talking about. It's important that you understand what I'm saying. Don't memorize. Make sure you're understanding things. Okay, maximum and minimum. Also called maxima and minima. And a maxima or minima is called extrema. There's a lot of different vocabulary that are synonyms that you have to understand. Now, this definition seems crazy, but you need to understand it. This form of questions will appear on AP tests, specifically in multiple choice. So make sure you understand what it is saying. So here's the definition of a maximum or a minimum. So f is a function defined on a set D containing point C. Now, what does that craziness mean? D is just a domain. It's like all the values where the function exists. And there's some C within that value. For example, on this problem, on this picture right here, D would be all the points from -2 to 2. So D would be the interval from -2 to 2, like the domain. That's the D. And C is any point. So there's a C. It's just some point in the domain of the function. Then they say, suppose you plug C into the function, and the y value there is bigger than or equal to the function for every other point in the domain. So let that sink into your head. The value, the y value, because f of c is the y value at c, is bigger than or equal to the function for every point in the domain. Clearly, hopefully, you're seeing that means this is the biggest point. There is no bigger point because it's bigger than all other points. Then we can say f has an absolute maximum value of f at c. At c. It occurs at c, and the maximum value is f of c because f of c is the y value. So that is absolute maximum, meaning in its domain, in its realm, in its world, there is no larger value. All right, and then similarly, how about absolute minimum? If you plug in some point C and that y value is smaller than every other value of the function in the domain, then you could tell this is the smallest y value. That's called an absolute minimum. Absolute minimum. Now that's supposed to be f at c. That's a autocorrect. So the minimum value is the function at c, and it occurs at the x value of c. Now sometimes they call absolute maximum and absolute minimum global maximums and global minimums because like the global is in the whole world. I'm the tallest mountain in the whole world. I am the whatever. So they call it global. And then you might have a local. I might be the tallest person in my house. That would be a local. So global, absolute. So those are other terms. Now, extrema, the extremes. You have two extremes, the super lows and the super highs. So an extrema can refer to either a maximum or a minimum. It's just the highest point and lowest point. So we're going to look at some examples of absolute maximums and minimums of these graphs. And there are some really important concepts, so pay close attention. So graphically, if we're looking, what is the greatest value of this first graph right here? And you'll notice there's 2 points, here and here. Using this definition, we would say c at -2 is greater than or equal to the function for all values of x, for all x in this interval. Is that true? Well, the y value right there, is it bigger than every other y value everywhere else? You might say, nope, right there, it's equal, but it has an equal in it. That's why it's equal. In this case, there's actually two absolute maximums, here and here. So two absolute maximums, they occur here and here. The values of c are -2 and 2. So the absolute maximum value is 4, but it occurs at -2 and 2. How about a minimum? Is there a c where the function at that point is smaller than every other y value? I claim here. There is my c. That point, f of that c is less than or equal to every other value of f of x in the interval from -2 to 2. Because that is smaller than all of these. So that would make f of 0 is the minimum value, and it occurs at 0. Okay, so the extremes, there are 3 extremes, 2 on top, 1 on the bottom. All right, let's look at this next one. Just quickly observing, there's the absolute maximum, there's the absolute minimum. On this third one here, the absolute minimum is pretty easy there. Now, where do you think the absolute maximum is? So the absolute maximum has to occur at some value of c where if you get the y value there, you can show it's bigger than all other y values. So there's got to be a point. But if you see this goes up forever, you cannot pick a point that's the maximum. If you say, okay, the maximum is right there. No, it's not. There's a point bigger here because it keeps going. And if you say, okay, I know the maximum, it's right there. No, because it keeps going. No, the maximum's there. No, because it keeps going. There is no point that is bigger than any other point. Because if once you pick a point, there's always one bigger because it keeps going up. So there is no maximum if a function keeps increasing. Now here's a tricky one. There's a minimum there. Now a lot of people might say, what? Okay, go ahead and pause. What do you think the maximum of this graph is? What do you think the maximum? Okay, a lot of people would say 4 is the max. I would say that's not correct because if you notice, there's an open dot there. 4 does not exist. When x is 2, y does not equal 4. It's an open circle. That point does not exist. This interval goes from -1 to 2. And just make sure you get notation. That bracket means you include that point. That parenthesis means there's a hollow point there. It does not include that point. So make sure you know that notation. But someone say 4 is the maximum. Well, if 4 is the maximum, then f at some c must equal 4. Because the maximum is the function at some point c, where c is in the domain. But if you look at this, 4, it doesn't exist at 4. It's an open dot. So you can't find a value of c where the function equals 4, because it never equals 4. Then someone says, okay, you're right on that. I say the maximum is 3.999. There's a point 3.999 like right below there, right there. So I would agree there is some value c. So there is some x value like, I don't know, somewhere right here, 1.9999, and then the y value here is like 3.9999, right? If you say that's the maximum, I say no, because I claim I know a value of f of x that's 3.9999. So whenever you pick a point as a maximum, I'm like, nope, I pick a point a little bit bigger. And so no matter what point you pick, I can always pick one bigger than you. So here's the takeaway from that. If there's an open-ended graph, There cannot be a maximum or minimum at that point. Because no matter what point you pick, 3.99999, nope, 3.99999 is bigger. Then you say, no, 3.9999999. I'm like, nope, because on this graph is 3.999999999. So you cannot pick a largest value. So this next graph, we don't need to talk about it. It's the same thing. The minimum occurs here. There is no maximum because you cannot pick a largest value. Does this have an absolute minimum? Yes, it does. The minimum value is -2, and it occurs when x is -2. Does it have a maximum? No, because at this point, it's an open dot. You cannot have a maximum open dot. Does this have a minimum? Yes. Does it have a maximum? No, because there's an open dot. So I might say, yeah, 2.999999. I say no, because this graph also contains 2.9999999. And this one here, go ahead and pause and talk to yourself and tell yourself where the maximum is and where the minimum is. Welcome back. I claim there are two minimums. The minimum is -4 and -4, and it occurs at -2 and 1. So there's 2 points that are an absolute minimum. And then the maximum, is it 4? No. There's an open dot there. There cannot be a maximum. It's not 3.999999999, because whatever you pick, I'm going to add one more 9, and I'm going to be bigger than you. So no maximum on that. All right. So hopefully you understand what an absolute maximum is, absolute minimum. The next topic, we have a theorem. You have to know this theorem. You'll be quizzed on this theorem. It's called the extreme value theorem. So there's a couple of conditions. First, for this to work, the function must be continuous. Secondly, it must be a closed interval. Okay? Must be continuous on a closed interval, meaning you have to have endpoints included. If that's true, this theorem says you will have an absolute maximum and you will have an absolute minimum. So a continuous function on a closed interval will have a maximum point, absolute maximum, and will have an absolute minimum. And just a side note, I'll be mentioning this later, but if you say minimum or maximum without saying absolute, it's the same thing. It's implied. What's the maximum value? Well, it's the absolute max. It's just the highest. It's implied there. So you don't even have to say absolute. It also, just saying maximum means biggest. All right, here are examples. And I want to point some things out here that are very important as we do this. These are all continuous. There's no, on all 4 of these, there's no holes, there's no jumps, there's no gaps, there's no vertical asymptotes. So all of these are continuous, meaning that, and they all include their endpoints. And they all have a max or min. Max, min, max, min, max, min, max, min. Okay? Now, here is the next thing that you have to know. If you have a continuous function on a closed interval, the max and mins will occur at certain places, either the endpoints or these weird points that we're going to define in a second. They're actually called critical points, and you will see what a critical point is. So let's keep going. More definitions. First, we did absolute max and min. Now local. What's a local maximum and a local minimum? So another word for local, sometimes they say, my brain just went blank, relative maximum, relative minimum. So the difference between absolute max and local max, let's look at our high school. Let's look at my classroom, even though we're not physically my classroom. If I found the tallest person in my classroom, we'd say, man, this is the maximum height in my classroom, locally, in my area. but chances are that person's not the tallest person at Garden Grove High School. At Garden Grove High School, we'd call the tallest person there would be the absolute maximum height. But in my classroom, we could have a local maximum height in my area. So local or relative to the people around me. So that's all that's saying. So the only difference between local and absolute, you're going to have a point C, but it's going to be on an interval I, not on the whole domain, just in an area, it's interval, a part of the domain. And we're going to have the same definition. If that value of C, the y value there is bigger than all the y values in the area, on the interval around that point, then it's the local maximum and it's the local minimum. So I will show you examples from 4.5. All right, this point, I should see if it says it here. Yeah, key thing, interior point. It cannot be an endpoint. Endpoints are not local maximums. Endpoints cannot be local minimums. It doesn't count. It has to be interior to the area. So this point right here, if you look at it, is it a relative minimum? Well, let's do the other points first. Right there, that point, we would say it's a local maximum because in its area, it's the biggest point. And some might say, but it's bigger over here. But that's the idea of a local or relative maximum. In its local area, in its relative area, it will be the largest point. So right here, that would be a local minimum or a relative minimum or minima because in its area, it's the smallest. Even though there's smallest points elsewhere, it is locally a minimum value. Now here, there are no higher points anywhere else. That is called an absolute maximum. But in its area, it's also a maximum. So therefore, it's also called a local maximum or relative maximum. So that point is both a relative and an absolute. Like suppose in my classroom, the tallest person in the school was in my classroom. I could say in this classroom, he is the tallest person or she. That's locally. But then we could also say this person is the tallest person in the whole school. That's the absolute maximum. So they can be both. Now the endpoint, that cannot be a local minimum because local minimums have to be interior points. They can't be endpoints. So that's nothing. It's not a minimum. It's not a local minimum. But over here, is that a local minimum? No, because it's not in the interior of the graph. But this would be the absolute minimum because it's the smallest point of anywhere on the graph. Okay, this example, it says for the functions given, identify locations of absolute maximum value and the absolute minimum value. Do the functions meet the conditions of the extreme value theorem? Okay, back to the extreme value theorem. That's the one that said if you have a continuous function on a closed interval, it has to have a maximum and it has to have a minimum. Extreme value theorem, extremes, like highs and lows. Well, the first one, does it meet the condition of the extreme value theorem? Is it continuous? Yep, I don't see any holes, jumps, or gaps, or vertical asymptotes. Does it contain the endpoints? Yes, there's solid dots there. So that meets the conditions of the extreme value theorem. So there has to be, according to that theorem, a biggest point and the smallest point. So where's the absolute maximum? I claim it's right there. Where's the absolute minimum? I claim it's right there. So that fits the extreme value theorem, and we do have a max and min. All right, B, does that fit the extreme value theorem? And the answer to me is no, because the extreme value theorem says I must be continuous, and we have a jump. And the extreme value theorem says it must be a closed interval, but our endpoints are open, so it's double whammy, does not meet the extreme value theorem. But that doesn't mean it can't have a max or min. We just don't guarantee it doesn't, but it might, Does it have a maximum value? Yep, that's bigger than null. Does it have a minimum value? No, because it looks like the minimum's there, but it's an open circle. You cannot have a minimum at an open circle. So that's that example. A lot of stuff going on here. Another definition. So make sure you're taking good notes. Good chance this will be on the quiz on coming up on the next class meeting. You have a new word, critical point, that needs to be in your vocabulary. So a critical point is an interior point, so it can't be an endpoint, but pretty simple. It's a value of x on the interior of your domain where the derivative is 0 or the derivative does not exist. So a critical point is a value of x where at that point the derivative is 0 or the derivative does not exist. Okay? I am going to do some examples. You could actually pause and try these and see what I'm doing with these, but we want to find the critical points of this function. Again, definition, where the derivative is 0 or the derivative does not exist. So go ahead and pause and try this. Okay, if you need a hint and you've come back to listen, we need to find the derivative of f of x. And my hint to you is going to be a product rule. So you can pause and try this again, or if you got it, let's just keep going. So product rule, you leave the first alone, take the derivative of the second, then you take the derivative of the first and you leave the second alone. So here I have my derivative. One of those cancels with one of those, and I get x plus 2x ln of x. Well, I want to know when this is 0 or when it's undefined. So what I'm going to do, I'm going to factor out an x. I get 1 plus 2 ln of x. Now, this will equal 0. If that's 0, it doesn't matter what that is. It's going to equal 0. So we set x equal to 0 as one possibility. Then, if this equals 0, 0 times anything is 0, so that will work also. So 1 plus 2 ln of x equals 0. So here's one possible solution. I'm going to take the other one, 1 plus 2 ln of x, and solve that for x. Subtract 1 from both sides, and we'll get negative 1 on the other side. Divide both sides by 2, and you're going to get negative 1/2. Now, this is where your trig skills or algebra skills need to come into play. To get rid of ln, the inverse function is e. I e both sides. E and ln cancel. So my other one is x e to the negative 1/2, which is 1 over square root of e. Now I'll explain that, making sure that you guys understand what just happened. The negative moves that to the bottom, and the 1/2 power is square root. And I will explain everything that's going on and make this make some sense to you and make some connections with critical points and see if you understand what's happening. And then let's look at what's going on here. So at x equals 0, that will be 0, but ln of 0 does not exist. You should know the graph of ln of x. It looks like this. This graph does not exist at 0. That's an asymptote. So since this point doesn't exist in the original function, it cannot be a critical point. So we only have one critical point, and that's it here. And to make some connections for you, here's our graph. What is a critical point? It's where the derivative is 0 or does not exist. Well, notice from this graph, at this point right here, what's the slope of the tangent line? That. It's 0. So that's why there's a critical point right here, because that's that value, and at that value, the derivative equals 0 at that point. That's how we found that critical point. Now at 0, I graph this. If you look, the function doesn't even exist at 0. So in the graph, that's why 0 is not counted. I want to look at a graph here. We're going to find critical points. We'll just look at this graph. From a graphical point of view, what are the critical points of this graph? Go ahead and pause and think about this, and then come back. Okay, I claim there are 4 critical points, and let me show you. I claim that's a critical point because the slope of the tangent line, oops, that didn't do what I wanted to do. The slope of the tangent line is 0. I claim that's a critical point because the slope of the tangent line is 0. I claim that's a critical point because the slope of the tangent line is 0. Now, I claim that's a critical point because that's a sharp point, and we know derivatives don't exist at sharp point. And again, let's look at the definition of the critical point. There are values of x where the derivative is 0 or the derivative does not exist. Well, I claim the derivative is 0 here, here, and here, and it doesn't exist there. All right, let's look at this one. Find all critical points. You can pause. Again, I say there are 3 critical points. Why? Here, because the derivative, let's get a different color. Here, because the derivative is 0. Here, because the derivative is 0. And here, because the derivative does not exist because it's a sharp point. So we have 3 critical points. So visually, you should know what critical points look like. I'm going to do more. Okay, let's look at this graph. Go ahead and pause and see if you can find any critical points. Okay, there's a critical point right there because the derivative does not exist there, because we know when there's a discontinuity, the derivative does not exist. Okay, this one here, go ahead and pause. Does the second one to the right have a critical point? Okay, now you're back. I say yes, there's a critical point right here because the derivative does not exist at that point because there's a sharp point. So that's a critical point. Let me see if I have any more good graphs to look at. We looked at most of these. Let's look at, we've already looked at these. Yeah, let's look at this one. Go ahead and pause. Where are the critical points of these graphs? Okay, coming back, I claim there are, well, let's look at the first one. There might be one right there. It's possible that the tangent line at that point is 0. Maybe. It's hard to tell. So maybe that does have one. Here, I claim there's a critical point right there because it looks like the tangent line is 0. Slope of tangent line is 0. Let me adjust that a little bit. The bottom left, I claim there's a critical point right there because it looks like the slope of the tangent line is 0 at that point. And then this one, I claim there's 2, one right there and one right here, because it appears that the slope of the tangent line is 0 at those points. So hopefully you're getting a feeling for critical points. We don't have to go back here. So I believe we did this one. Critical point, critical point, critical point. Critical point, critical point, critical point, critical point, because the tangent line is 0 there. Critical point, critical point, critical point. Critical point, critical point. All right, let's do this other example. I know we're bouncing around a little bit, but this example, find the critical points of this function on the interval from negative 2 pi to 2 pi. So give that a shot. All right, we need to find the derivative of g, and it's a product rule. So if you didn't recognize product rule and you want to try this problem again, you can pause and try it again. We leave the first alone, take the derivative of the second. We take the derivative of the first, and we leave the second alone. So we're going to get minus sine squared x plus cosine squared x. Now, there is an identity, and I doubt many of you remember this, but Cosine squared minus sine squared is the cosine of 2x. Now, if you didn't know that, this would have been a hard problem. But now that we have that, go ahead and see if you can find the critical points. All right, we want to know when the derivative is 0, because that's a critical point. Well, at what angles? So 2x is our angle. What angles have a cosine of 0? You should know 0. No, sorry, not 0. Pi over 2. If you don't know your unit circle, it's going to hurt you. So you might want to watch that video I put out on unit circle. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. And I'm going to stop there because look at my domain. Well, actually, I should keep going. Well, we'll see what's going to happen here. I'll go farther. 9 pi over 2. Now, I want to solve for x. It's the x values of the original function here. So to solve for x, I need to divide both sides of this by 2. So we're going to x equals pi over 4, 3 pi over 4, because I'm dividing all these by 2, 5 pi over 4, and 7 pi over 4. And we would stop there because if we go further, we're going to be outside of 2 pi. Oh, I'm a liar, liar, pants on fire. I didn't want, okay. We would have to do plus or minus on all of these. And we would get, I'm sorry, plus or minus on all these. I didn't graph the whole thing either. I forgot to change it. But we would get a duplicate on this side and all those same points on this side that are symmetric. So those are our 4 points. And you can see from the graph, it appears that's where the derivative is 0. I'm kind of butchering this a bit, but hopefully it's close enough. Yeah, that's not just flat. Falling flat on that. There we go. So 4 critical points. Points where the derivative is 0. Now, here is the next huge takeaway. Where do relative max and mins or local max and mins occur? They always occur at critical points. You're going to have a million questions this year asking you to find relative max and mins. How do you find it? You must know if you have one, it's going to be at a critical point. So to find relative max and mins, you have to find critical points. So I wrote, in other words, if you want to find a relative max and min, you must look at the critical points. But here's a caution. Some people assume I found a critical point, therefore there's going to be a relative max or min. That is not true. Just because you have a critical point, it doesn't mean you have a relative max or min or a local max or min. And I'm going to show you an example why. Do I have one that I can quickly show you? I don't, but I think I have one. If not, I will give you 2 examples. So let me go to some blank space. Just because you have a critical point doesn't mean that you have a relative max or min. I'm going to give you 2 graphs that perfectly illustrate this. So you can have a graph of x cubed. If you graphed it, it looks something like this. Now, we're going to discover that at that point, the slope of the tangent line is 0. You're going to say there's a critical point there. But clearly, that's not a relative max or min. That point is not bigger than all points around it or smaller than all points around it. So therefore, just because the derivative is 0 or you have a critical point doesn't mean you have a local max or local min. But you have the possibility. Here's the other function I want to do. I'm going to do cube root of x. Cube root of x looks like this. Let me just erase this and do it for you. What does the... I should have started all over anyways. The cube root of x looks like? Well, it's the same function, but now it's going to be sideways. It's going to go like that. That's kind of off, but close. Right there, if you drew the tangent line, it's vertical. A vertical tangent line, the derivative does not exist because the slope of a vertical line does not exist. So that point is a critical point, but clearly it's not a relative max or min because in its area, it's not the biggest or smallest point. So the point is, very important point, just because you have a critical point doesn't mean you have a relative max or min. But the other way is true. If you have a relative max or min, it's got to be at a critical point. And we're just going to look at examples to reinforce this. Okay. That is a relative max right there. But you'll notice the tangent line has a slope of 0, therefore the derivative is 0. That's a relative min, but the slope of the tangent line is 0. So therefore it's a critical point. Here, slope 0, derivative is 0, critical point. Here, slope is 0. So every max or min, in this case, relative max or min, has a derivative of 0. Let's look at more. It's a relative max, but the slope of the tangent line is 0, so the derivative is 0. Relative min, slope of the tangent line is 0, so the derivative is 0. That's a relative max, but the slope of the tangent line is not 0. But because there's a sharp point, the derivative does not exist, making that a critical point. So every relative max or min is a critical point. Relative max, relative min. Derivative 0, derivative 0. This one, that's a relative min, but the derivative is 0. We found that. More examples. This one, critical point, or relative max, relative max, relative min, relative min. All four of those points, the derivative is either 0 or doesn't exist. Another one, let me erase that dot I have there. I claim this is a relative min. That's weird, because in its area, in its region, it is the smallest point. Where does that relative min occur? It occurs at a critical point, because at C, the derivative does not exist, because we know derivatives don't exist at discontinuities. Same thing, there's a local maximum there, but that is a critical point because the derivative does not exist there because there's a sharp point. So hopefully this is sinking in. So to find relative max and mins, you have to look at the critical points. But if you have a critical point, does not mean it's a relative max or min. Okay, here is the end of our lesson. So here's an important thing. This happens all the time on FRQs. I guarantee you're going to have a problem of this kind on your AP test. So remember, the extreme value theorem says that if you have a continuous function on a closed interval, you know you're going to have a max or min. Well, here's the next thing you have to know, and you'll be quizzed on this. How do you find a max and min of a continuous function on a closed interval? So here's what you need to know. Maximums and minimums that are guaranteed by the extreme value theorem occur either at critical points or endpoints. Okay, let me show you. Go back to our original max and mins. Where are the maxes? At the endpoint. Where's the min? At a critical point. Let's look at this. Where's the max? At the endpoint. Where's the min? At a critical point. Where's the maximum? This one didn't have a max, but where's the min? Here, it's at a critical point. So we're going to be sticking with functions on a closed interval. Where's the max? At an endpoint. Where's the min? At an endpoint. Where's the max? At a critical point. Where's the min? At an endpoint. Where's the min? At a critical point. Where's the max? At the endpoint. Where's the max? At a critical point. Where's the min? At a critical point. So whenever you have a continuous function on a closed interval, the max and mins occur at critical points and endpoints. Where's the max? Right there. But that's a critical point because the derivative doesn't exist. Where's the min? At an endpoint. Where's the max? Right there. Endpoint. Where's the minimum? Right there, which is a critical point. So I think I've beat this topic to death. So if you want to find the max or min of a continuous function on a closed interval, find the critical points, then find the y value of the function at the critical points and the endpoints. Then you just pick the biggest one is the max, the smallest one is the min. So I summarize down here. In other words, max and mins of continuous functions on a closed interval can only occur at critical points and endpoints. So therefore, find the y values at critical points and endpoints. So we're going to do two examples. First, we'll do example A right here. So you can pause this and try this. If you want to get hints, just go ahead and unpause and watch for a little bit and then pause again. Restart, and you just go back and forth and kind of work your way through this. All right, so find the absolute maximum and minimum of the following functions. Well, it's a polynomial, so we know it's continuous. It's on a closed interval, so by the extreme value theorem, we know it will have a max and will have a min. And then someone taught me max and mins can only occur at critical points and endpoints. So I already have my endpoints. Done. I need to find critical points. Again, what are critical points? It's where the derivative is 0 or undefined. So I'm going to take the derivative of the first function, part A, that's 4x cubed minus 6x squared. I'm going to factor out 2x squared, and that'll leave me 2x minus 3, double check. That's 4x cubed, bam, we're good. That's going to be minus 6x squared, bam, we're good. So what is a critical point? Where the derivative is 0. To be 0, either 2x squared must be 0, or 2x minus 3 must be 0. If I solve for x, I get these two critical points. So, how do I know where the max or min occurs? Well, it's going to be the biggest y value and the smallest y value. So I'm going to plug into my function the endpoints, and I'm going to plug into my function the critical points, because I learned max and mins occur at critical points and endpoints. Why do I plug it into the original function f? Because f tells me the y value. The derivative tells me the slope of the tangent line. The function tells me the y value. If I plug those in, magically, I know the answers are 32, 0, 27 sixteenths, and 0. What is the biggest value? 32. So the max is 32 and occurs at x equals negative 2. Where's the smallest values? 0. So the min is 0 and occurs at either 0 or 2. Now we're going to look at the graph to verify this. I graphed this for you. So we're going to kind of look at everything. So what is that telling us? Look, at 0, the slope was 0. But it's not a max or min. It's not. What happens at 3 halves? 3 halves is right there. Look, the derivative is 0. That's our critical point. Now, we found, I made a mistake here. It looks like 3 halves is negative. I think it's negative 27 over 16. I think I blew it. Okay, I don't want to waste your time. I'm going to assume that's, no. Yeah, I'm going to assume that's negative. I think I messed up. And so I'm going to change everything I wrote here. Therefore, and I may have totally messed this up, but you get the idea. So the minimum value is negative 27 over 16. It occurs at x equals 3 over 2. So I stand corrected. So that's the absolute minimum. And we found it by, not with the graph, because you're not going to have the graph when you do these. We found it by checking the y value at the endpoints and critical points. Now, where's the biggest value? Right there. It happens at negative 2. That's what we found. At negative 2, you have a maximum value. So that's using derivatives to find critical points and testing critical points and endpoints. So you have one more, actually we have two more examples. Example 4b, go ahead and pause and see if you can find the absolute max and minimum of this. So g prime of x, product rule, because I'm multiplying two things together. So I leave the first alone, and I take the derivative of the second. And then I take the derivative of the first, the power rule, I bring the 2/3 in front, decrease that by 1. I don't know why I put parentheses around there. Decrease that by 1, I'm going to get negative 1/3. And I leave the second alone, so I'm going to have a 2 minus x. Now, here's where it gets weird. They both have an x. I'm going to factor that out, but I don't like that fraction, so I'm going to factor that 1/3 out also. So I'm going to take out an x and a 1/3, but I take the lowest power of those two, so I'm going to factor out the negative 1/3. And then what's left? So I still have the negative, but I'm going to have a negative 3. And why? Because this and that have to get me a 1. So 1/3 times negative 3, that gives me a negative 1. And then x, I claim as the first power. Why? Because when you multiply these two, you have to add the exponents. Negative 1/3 plus 1 gets you 2/3. So it's going to be 1. So the 2's left because I took out that 3 in front. I took that out, so that's gone. And I'm left with 2 minus x. So that negative moves it to the bottom. So I'm going to have 1/3, and that's a cube root of x because it's a 1/3 power. Negative 3x, distribute the 2. I'm going to have a 4 minus 2x. So to simplify, I'm going to have a minus 5x plus 4 all over 3 cube root of x. There is my derivative. Wow, all that work. Now the next question, we have to find critical points because we know max and mins occur at critical points or endpoints. So how do I set this equal to 0? A fraction is equal to 0 when the top is 0. You have to know that. So negative 5x plus 4 equals 0. If I solve for x, I get 4/5. There is one critical point where the derivative is 0. So how do I get an undefined? A fraction is undefined if you divide by 0 or the denominator is 0. So I'm going to set the denominator equal to 0. Divide both sides by 3. Cube both sides. So I have two critical points. At 0, my derivative, I'm dividing by 0, it's undefined. When x is 4/5, if I put a 4/5 there, this becomes 0, my derivative is 0. So two critical points. I have found two critical points. But what's the question asking for? The absolute maximum and minimum value. So next, the endpoints were negative 1 and 2. So I need to find the y value at negative 1 and at 2 and at my critical points. So I'm going to find the y value at 0 and the y value at 4/5. And I pre-did these, so hopefully this time I didn't mess up. I don't know, I messed up last time. And I get these values. So what is the maximum? I claim 3. The maximum value is 3 and occurs at x equals negative 1. What's the minimum? I have two minimums, 0. The minimum value is 0 and it occurs at x equals 0 and 2. So let's look at our graph and see if it matches up. Okay, check this out. At 0, we said the derivative did not exist because I'm dividing by 0, right? Remember that? Look, at 0, we have a sharp point. Derivative does not exist. At 4/5, the derivative was 0. 4/5 is right there, and we can see the slope of that line is 0. So that matches that. So we had two critical points, here and here, 0 and 4/5. and the endpoints. Where is the maximum value? Here, at -2. And we found that, or excuse me, -1. At -1, we had a maximum of 3. That matches up. And our minimums occur there and there. It's 0. We found it's 0 at 0 and 2. So bam, that's awesome. Hopefully this is sinking in. And these concepts, you just have to make some flashcards. And this last example, I will do this. Hopefully you're not getting too tired. You don't have to watch this last one if you feel like you've got it. But a stone is thrown vertically upward from a bridge that's 80 feet above the ground at the speed of 64 feet per second. The height above the ground, its height above the ground t seconds after launch is this. So this is the position function, its height. When does it reach a maximum height? And what is the maximum height? We're trying to find a maximum. We should know maximums occur at critical points and endpoints. So I take the derivative and I set it equal to 0. Well, I subtract 64 from both sides, divide both sides by 2, and I get 2. So think about this. When you throw a stone, it's going to go up and it's going to go down. So the maximum is going to occur at the critical point. So I don't even have to check the endpoints because I know the maximum is not going to occur at the endpoints. I'm on a bridge, right? I throw it up and it falls to the water or the ground down below. So in this case, using logic, I could assume that the critical point I found has to be this point, and that's the maximum. So it occurs at t equals 2. That's when. And what is the maximum height? I plug in 2 into that. And I did not pre-work these out, so hopefully I don't mess up too badly. 16, that's -64 plus 128 plus 80. That's 64 plus 80, 144 feet. I hope that's the answer, or if not, I'm embarrassed. But that's the end of this long lesson. Bye-bye.